We're going to define the concept of magnetic flux through a surface, and you'll find it quite analogous to the concept of electric flux through a surface. So the Greek letter capital phi here, phi sub b for magnetic flux. Going back to electric flux through an open surface, defined as phi sub e, that is the open surface integral of the E field vector at every patch of the surface, dotted with the local surface area vector dA pointing orthogonal to that surface. And recall that we have to pick like a front side for the surface, so dA points out the front side. Likewise, the magnetic flux through a surface can be defined as phi b here, the open surface integral of the magnetic field vector at every point on the surface, dotted with the local surface area vector dA pointing perpendicular to that surface and pointing out from the front side of the surface. We have to define a front side and a back side. That's if our surface is open. If the surface is closed, then there is no front side and back side in the same sense. Instead, we have sort of an inside volume and an outside volume. So if we do the closed surface integral of E dot dA, so this would be the electric flux through a closed surface, we always find that that value is proportional to the charge enclosed inside that surface, so the total charge in the volume closed off by that surface. And that's Gauss's law. The magnetic flux through a closed surface, so we have the circle icon around our integral symbol there to indicate a closed surface, we find that that value is always 0 through any closed surface in any situation. That's our no magnetic monopoles law. These two pictures illustrate the difference. I've got some point charge here generating an electric field, and here's some other field lines, electric field lines, and a dotted line indicating some closed Gaussian surface, some Gaussian bag. We see that the electric field lines generated by the charge that's inside the region, those leave and don't come back, but there are some other field lines that enter and then leave, enter and then leave. So these lines leaving represent positive flux. That's positive flux here and here as well. So positive flux leaving our surface at all those locations, but then negative flux at these two locations here, where the field lines are coming inwards. Okay, so the net flux here is non-zero and proportional to that charge enclosed. That's Gauss's law. If we take a similar Gaussian bag but put it in a region where there are magnetic field lines, these B field lines instead, the no monopoles law says that B field lines are always closed loops. So for every B field line that enters our region, negative flux there, entering here and entering there, that would be negative flux through the surface at all those locations. We have positive flux for B field lines leaving the surface, exiting the surface at all those locations. Every field line that enters somewhere leaves somewhere else. Thus, no net flux through any magnetic surface. The B field lines, no net magnetic flux through any closed surface. The B field lines don't begin or end anywhere, they're closed loops, unlike the E field lines, which begin and end on point charges. Okay, two examples. First example here, imagine we've got a region with a uniform B field kind of pointing up and to the right at this angle, and we're going to put a ring in this region. So we're imagining a path, a circular path, bounding this open surface that I've colored a little bit in orange there. So you have an open surface bounded by this ring. I would like to compute the magnetic flux through this open surface. So we'll have to define a front side and a back side. The top here will be the front side of our surface. Underside that we don't see will be the back side. So our little dA vectors at every little patch of surface area point out perpendicular to the surface, making right angles there, right angle, making right angles to the surface, pointing out away from what we've defined as the front side. So a little dA vector at every point on the surface. And then we look at the magnetic field vector at all of those locations as well. And what we're going to do is dot that the local magnetic field vector with the dA vector at that point. Okay, so if B is uniform, so it has the same magnitude, it makes the same angle with all those dA vectors, then our dot product is easy here. B dot dA just gives us B dA cos theta. B is uniform, and the angle is the same at all these locations. So in this example, we could pull out the B field magnitude, pull out cosine theta, and just add up the areas of all these little surface patches. Add up all those patch areas, and we would get the total area of our open surface. If it's a circle with radius big R, then that would be pi r squared for the total area, and that would be our magnetic flux through that open surface. Second example. Here, let's take that same, let's take another ring, circular ring, enclosing or a ring sort of bounding this open surface. And so that ring has radius b here. If we're looking straight at it, so our dA vectors are pointing out of the page, little dA surface areas with dA vectors pointing out of the page. And suppose there's a B field confined to just this region only. So a uniform magnetic field confined to this region, so B field pointing out of the page, but just in this region. So no B field over here, only B field in here, inside this circular region of radius a, little a. So in this case, if I want to find the magnetic flux through this entire open surface here, then I can break up that open surface into two parts. The portion of the open surface where there is B field, and then the remaining portion of the open surface where there is no B field. So we're sort of cutting out that little section, that little circular section there where there is actually B field. So for this integral, B is 0 at this location and all these locations out here. So if B is 0 out there, then there's no magnetic flux through all these parts of our open surface. That goes to 0. We only have magnetic flux coming through this region right here. So we'll do B dot dA in this region. If B and A are both out of the page and the angle between them is 0 degrees. Sorry, this should say cosine of 0 degrees. Since B and A are both out of the page is 1. And if B is uniform across that surface, then the B magnitude comes out. And we just have to add up all the surface area patches, all the little dAs inside this region only. Add up all those areas, and we'll get the total area of this region where the B field is located. So if it's a circular region of radius little a, then pi a squared would be the magnetic flux coming through the whole open surface. So one thing I wanted to emphasize in this example is that even though the whole open surface has a cross-sectional area of pi times little b squared, the area that matters is this one where there actually is field. So the flux through this whole thing depends on pi a squared, not on pi b squared, since there's no flux out here, only flux coming through this region. Lastly, the units on magnetic flux, based on our definitions here. The SI unit, just as a reminder on electric field, we can put together our SI units for electric field and area. So newtons per coulomb times meters squared. So Newton meters squared per coulomb, SI unit for electric flux. For magnetic flux, we'll take the unit on magnetic field strength. So T teslas times meters squared. So Tesla meters squared are units for magnetic flux. This has another name. 1 Tesla meter squared is defined to be equivalent to 1 Weber. Capital W, lowercase b, as an abbreviation, is named for an abbreviation for the name Weber. So a Weber is equivalent to a Tesla meters squared in the SI system.